Okay, so we're back to part two, and now we're trying to figure out how X1, which is the indifferent consumer, how that is determined. So, consumers who reside at distance X1 from the shop are indifferent from buying and not buying, meaning the full price has to be equal exactly to her willingness to pay. So it's this one. Now, as a reminder, we shall look at this, right? And I'm going to put this back in the center. And then I'm going to increase its size. There. This is kind of like the center. So we're trying to figure out what X1 is. Oh, there, it's already there. What X1 is, and which is here on the right and here on the left. That's the intersection between between the total price, which is the height here, which is the price of the good that's being offered. This is how the firm makes money. And then this one, which happens to be the cost that has to be paid by the consumer, because the consumer has to travel from X1 all the way to the middle. And that cost is TX1. Okay. So mathematically, it's just to equate those two things, which will give you the value of X1 in terms of V, whatever the price is, and T. The indifference condition will also give you demand, because like we said, the people who will buy are on two sides of the location of the town, not the town, but the store. Consumers on the left and the right hand of the market. The number of consumers willing to buy 1 unit of the product at price P is 2 times X, which is two sides of the X because it's symmetric, times N. Because remember, consumers are uniformly distributed. So in this picture here, the entire consumer base is N. So the share of the street from X1 on the left to X1 on the right, say this is like 80% of the street, then that means 80% of the consumers are going to buy from you. Okay. Now, with that said, the total demand for the monopolist was one shop. So that's why you have P1 and 1 here for the 1. That's this one. And if you substitute the indifference condition, it becomes this. And what's interesting about this is that you can see that the demand function here is basically the usual demand function that you might expect, especially in this class, wherein the demand is linearly a linear function of price, and it's negative, of course. Right? And aggregate demand increases as the monopolist lowers its price. Okay? Particular, if the price is like 0, he would never set at 0 because he would not earn money. But if it were, then you're basically selling to everyone. Well, everyone that's reaching the indifferent consumer. So it's 2NV over T. Okay. And as you can see, lowering the price will increase your demand here. All right. So what is the highest price that the monopolist can set and sell to all end customers? So this, if you notice, this is now 1/2 because the monopolist is in the center. It's 1/2. So that's why X is actually 1/2 here. So we know what X is. You then have to lower your price in order to do it because the price is the only thing that you can manipulate. So T over 1/2, this is like given exogenously in the model. So you have to lower your price such that P plus this transport cost is less than V or equal to V. Now, here's the price for end consumers and one store, which is essentially this one. Okay. Okay. Because again, for the indifference condition, this is actually equal to V, right? The price they'll want to increase the price until price is exactly equal to V minus T plus T over 2. V minus T over 2, which is this one. So the monopolist profit, let's say that there's a marginal production cost of C, setup costs per outlet is F. And if you just replace everything, it becomes this. So what do you notice here, just looking at it? If it could control T, it would like to. So it would like lower T as much as possible, because T is the thing that stops it from increasing the price. A lower T means a higher price, means a higher per unit margin, per customer margin. But from the perspective of the monopolist, it can't really affect T. So NV minus T over 2 minus, this is all just numbers, essentially. Okay. Given the fact that you want to sell to everyone. Okay. So that's one of the constraints here, that this expression here presumes that you'd want to sell to everyone. Okay. This is exactly how the price was determined. So confirm that the location of the single shop is at the center of town. This is the location that makes it possible for the single outlet to supply the entire market at the highest possible price. Okay. So I think we've shown that also, that the more, say, to the left it is, if you wanted to supply all the way down here, then you'd have to decrease the price for this one to reach all the way out there. Now you can have multiple outlets, and here I'll just run through the idea because it's literally all the same. Here there are two shops. You would want to evenly divide the market, basically. First shop is here. Second shop is here. They are not competing because look, the indifference condition is exactly met by two of the stores. So they're essentially sharing the market, with one shop getting 1/2 and the other shop getting 1/2. So the crucial thing here is that what happens to the price? Well, because X is now 1/4 instead of 1/2, right? Or X1, right? Remember the indifference condition, X1. V minus T over 4, it's T over 4 now. So compare that to when there's one store. So V minus T over 4, compare that to V minus T over 2. And you'll find that, given size of T, that the more stores you have, the higher the price you're able to sell. And that's because consumers don't have to travel that far. They don't have to pay this utility cost, and therefore you can raise your price and therefore make money from selling, make more money from selling. The monopolist output is now this. So exactly this, the only thing I wanted to point out that's different, other than the price here, is the fact that 2F is now your setup cost. With 3 shops, maybe you can see a pattern. Now it's V minus T over 6. You are dividing it again into 3. So that's why it's T over 6. And the monopolist profit is the following. See, now you're dividing it into 3. 1, 2, 3. There's no competition here because exactly these guys are the indifferent consumers and they don't really care if to move from here to here. So they're not competing with each other to get more market share. So with N retail outlets, this, and this, the price that can be charged for supplying the entire market is the following. So I invite you to add in the numbers. For example, if it's N is equal to 1, it's 1/2. If N is 2, then it's 1/4, etc. And then in general, for the N case, it's this one. Where the decision really here is for the monopolist, what should N be? As you can see here, there are two conflicting forces, right? As we said, if we increase the N, this whole thing goes down. The price, which happens to be this, goes up. So that's a reason for having more stores. A reason for not having more stores is each store will cost you F. Okay. So that's the problem. And it says here that even without scope economies, remember, scope economies are a cost-based factor with regard to the number of stores or the number of varieties. Yeah. Here there is no cost-based reason. F is linearly increasing with the number of stores. But there's still an incentive because the price per unit of the price for the good goes up, right? As the more stores there are. Okay, so maybe in class we can figure this out, derive this. What we're basically doing well, first you get the difference of the profit at n+1 and n-1, which is this. So this is an exact solution. But if you wanted like a calculus-based solution, you can just simply get the derivative of this one, which is something we could do in class. And then it will give you this expression. So look at this expression. Monopolist balances the increase in price and revenues against the additional setup costs. If n is large, f is small, and t is large. Those are the reasons for having many stores or many varieties. Okay. Okay, so remember we've established or we've assumed that you wanted to actually serve the entire market and merely partition the entire market based on the number of stores. Now, if only part of the market is served, then each retail outlet is effectively a standalone shop whose market area does not touch the remaining outlets. Okay. Which means there are some parts of the street which are not served. So here's an example of that. So here's shop 1 and here's shop 2. The price here is higher because you're not serving everyone, but the idea here is that if the price is higher, these guys stop buying, all of these guys stop buying, all of these guys stop buying. So the question is this situation with a higher price but fewer customers better than the situation up here where, just see it, okay? Let's look at this one. Where this one, you have to lower the price, but now you get to serve everyone. So if you can imagine it, a higher price here, going up like that, that means you serve fewer people, right? Now, ano yung mas mataas? It turns out that the profit maximizing price when only part of the market is served is V plus C over 2. That does not depend on the number of products or product variants. Okay. So this is sort of the price wherein you don't have to sell to everyone. So you don't have to equate the V to the highest possible price. Okay. So this is the derivation, which we can go through in class. We can like jump through this. This is basically a calculus thing, which is you get the first derivative of this with respect to P. And then that will give you the following. Okay, so now what determines if the entire market or not will be served, right? If that price is better than this price, which is the N store analog. So serving the entire market with N stores is better than supplying only part of the market, provided this. And this requires the following. Ultimately, V must be big enough such that it's bigger than the cost of producing the good plus transport cost divided by the number of stores. Okay. So it can't be that the transport cost is that high. If the transport costs are that high, then maybe it's not a good idea to sell to the entire market. And instead, it would just be a better idea to sell only to a subset of the market. And that's what this summarizes here. So intuition when the consumer reservation price is low relative to the production and transportation costs. When there are few outlets trying to supply the whole market, gives the monopolist a very low margin over operating costs and could even lead to selling at a loss. When the reservation price is high relative to the cost of production and transportation, and there are many outlets, the price that allows the monopolist to supply the entire market is high enough, and it allows reasonable margin over costs. Okay. So now we go to our next topic, which is the optimal number of product varieties. So what have we learned so far? A monopolist who wants to sell to everyone has a reason to have a lot of varieties, because for each variety that he has, it allows him to increase the price, because the more varieties or more stores there are, the closer you are in general to the consumers, the less costly it is for them to travel to you to buy your product, and then that means you are able to raise your price in response and still able to get them to buy from you. Okay. That raises the question whether the monopolist provides the degree of product variety that is consistent with maximizing welfare. The optimal variety of products offered, what is the degree of product variety that maximizes total surplus, which is, again, consumer plus producer. So now let's go to optimal here in the sense of maximizing total surplus. So you have N outlets. Your consumer surplus is the following. NV, which is the value of the market, minus NP, which is the price at which people are buying the products, minus TNN, which is the transport costs associated with N stores. Meanwhile, profits are the price here times N, which is the revenue. So whatever the consumers are paying, that's just whatever, that's all that's being transferred basically to the firm, to the monopolist. Minus NC, which is the marginal cost of production. Minus NF. And this again is the per store fixed cost. The total surplus is just the addition or the sum of them, and then N is this, minus this, I should say, minus transport cost minus NF. At total surplus. Now, if you can notice that N, small n, only appears in two places, transport costs and setup costs, right? So the more stores there, let's look at the trade-off again. The more stores there are, the less the transportation cost is, because the more stores, the more closer stores are to the consumers, the less they have to travel. But then a high N would mean a high setup cost, a high total setup cost. So this is again is similar. This is similar, but not the same as the monopolist problem. So this is the monopolist problem, right? In the monopolist problem, higher N means a higher price. That's good for the monopolist. But a higher N means a higher F. So as you can see here, before I move on to the next slide, you can see that the profit-based number of stores is different from the optimal total surplus-based number of stores down here, because they're maximizing different things. Okay, so maximizing the total surplus is equivalent to minimizing the sum of transportation and setup costs. Note that the monopolist always spaces its shop. So now we're trying to figure out what the TN is, right? What it is. Okay, so first, the whole idea here is, so this is one shop, and what we're trying to do is getting the area under these triangles, and these are the dollar or peso values of the transportation to move from wherever this is to the store. And if you follow this is basically just a triangle argument, and then you multiply it by 2. And then you multiply it by 2. What else? Then you multiply it by N. This is multiplying it by 2. And then multiplying by the number of shops, because they're small n shops, right? So this is the total transportation cost for n shops. So now what you want to do is minimize this guy. Okay. Where again, look at the trade-off here. As n goes up, small n goes up, this thing goes down, so that's good. But if n goes up, this guy goes up, so there's a trade-off. So if you want, you can do it this way. Cn plus 1 minus Cn, right? Then you can do it this way. And then it gives you this expression. You can use calculus to get a similar expression. And the point here is, under a profit maximizing only scheme, if you leave producers, specifically the monopolist a free hand to determine how many stores, then he will have too many stores, because this number is going to be bigger than this one, because 2 is smaller than 4. Okay. So the monopolist has an incentive to expand product variety even when the social gains from doing so have been exhausted. The monopolist chooses too much product variety, and this is essentially because of the effect of the price. It wants to have a lot of variety because the price goes up and total revenue goes up. Okay. You might ask, why does total revenue go up when price goes up? Kala ko ba there's a trade-off? Well, here we are selling to everyone. So N is given as a total, right? So we are selling to everyone. So when the price goes up and you sell to everyone, that just means your total revenue goes up, because each person pays more. Okay. So that's why the monopolist has an incentive, because the number of stores simply increases the price, and the number of stores, and given the fact that you're pricing such that you're selling to everyone, that means the total revenue will have to rise. Okay. So a monopolist offers too much variety because it maximizes profits and not surplus. Okay, so I'm gonna let you read this. It's basically similar to what I already said. All right. So now I think this is the last topic in the vertical model, horizontal differentiation model. Horizontal differentiation with price discrimination. This is interesting. If the monopolist delivers the product, he knows who is who by their address, right? So when that happens, what will be the response of the monopolist? Okay. So there'll be uniform delivered pricing. You charge each consumer the consumer's reservation price, which again here is V. So everyone has the same reservation price. They're just located differently, right? In different spots on the line. The firm charges all consumers the same price and absorbs the transportation costs in delivering to them. Discriminatory pricing, because price does not reflect the true cost of supplying consumers in different locations. Okay. So even if the price is the same, right? Number one, this is like perfect price discrimination. You are essentially getting all of the V. And in getting all of the V, you're just paying for all of the costs. And the costs happen to be both the cost of production and the cost of getting the products to the consumers. Now, will the monopolist supply each consumer? Okay, under this scenario. And retail outlets are evenly spaced. C T over 2N. So this is the general I will sell to everyone situation. Remember this? Transport and production costs that firms incur in supplying the customers located the farthest away from the retail point. For positive profits with price discrimination, it's the following. This one. For positive profits without price discrimination, it's this one. Now, where did we get this one? Remember, we did the optimal I won't sell to everyone computation earlier. I just wanted to point that out. It's this one. Remember this? Where is it? P star. Where is P star? P star. There you go. This one. which happens to be related to this one, right? C over T over N. Yeah, we can go back there. All right, so without price discrimination, this is the condition, and with price discrimination, it is this condition. Therefore, more consumers are served since the condition for positive profits under price discrimination is weaker. Why is it weaker? Because it's more likely for this to be met because 2 is bigger than 1. Now let's talk about the optimal number of retail outlets with price discrimination. The profit of the firm is the following: NV minus NC minus, again, this is the cost of providing for N firms selling to everyone. And this happens to be like the sizes of the triangle times 2 times the number of stores, etc. We already derived this. Plus NF, which is the setup cost. Okay. So if you notice, what's different here is that price is no longer a function of N. Why? Because we have uniform pricing. Okay, uniform delivered pricing. Everyone pays exactly B, so we get all of their willingness to pay. So there's no further benefit from increasing the number of stalls. At least from the price side. Of course, the whole problem here is trying to figure out how many stalls there ought to be. Right? All right, so this is with discrimination again because this has no N there. And you're selling to everyone. Okay, NVS total revenue is fixed, right? Because selling to everyone. NC is the total cost. T and N is the transport costs. And F is the setup costs. If you remember, this looks exactly like the optimal number of outlets for the situation in social welfare. You're just minimizing your costs of transportation and setup costs, which will give you the following, which is exactly the social optimum. So with perfect price discrimination, the firm expropriates all consumer surplus. And the degree of product variety that maximizes total profits equals degree of product variety that maximizes total surplus. So interpreting transportation costs in the product or characteristic space, price discrimination, product begins with a base product, then redesigned to customer specifications. The firm produces a band of horizontally differentiated products. The transportation cost here is the additional cost incurred by the firm in adapting it to the consumer's specifications. Remember, in this case, we, the monopolists, are the ones delivering to the consumers instead of them coming to us. So the transportation cost here is us adopting, changing our product to reach individual consumers. So long as the product design is under the control of the producer, he need not charge the full cost of the design change. By making a person choose among several options, what the salesperson is doing is making you reveal your actual address. Okay, so once I know where you are there, then I can basically offer you offer you a package such that I get all of your surplus, and I can absorb whatever costs it needs, transportation costs it needs to match your exact specifications. With flexible manufacturing systems, it's easy for firms to offer this type of product customization. And that ends our horizontal discussion. There's another video for vertical product differentiation. And I'll see you there.